It used to take quite a bit of time for a design idea to move from an engineer's brain to prototype to production. Thanks to advancements in additive manufacturing and technology, components and products have been able to come to market faster and more sustainably. Today, we're going to dive into additive fusion technology, or AFT, in 3D printing and additive manufacturing. Joining me today is Martin Eichenhofer, CEO and co-founder of 9T Labs in Zurich, Switzerland, a maker of this technology, which allows for the manufacture of strong, lightweight, and sustainable products using continuous fiber components. Thank you for joining us, Martin. Would you like to give us a brief little overview of 9T Labs and how it got its start?
Yeah, thanks. You already gave part of the introduction, maybe just where it's all started or where we come from. So we're Switzerland, Zurich-based startup. We come originally from ETH Zurich, the technical university here in Zurich, Switzerland, and that's where it started. So we used to work with robotic arms and working on additive manufacturing of continuous fiber composites in my PhD time, and we spun out 2018, so a little bit over, close to 6 years now. And we are now a little bit over 50 people here in Zurich, Switzerland, and we also have an office in the US, in the Boston area. So yeah, happy to be here and happy to elaborate more on the technology and what you might ask me.
Great. All right. So my first question is, what are the fundamental principles underlying additive fusion technology in 3D printing, and how does it differ from the other additive manufacturing processes?
It's a good question, and it's actually a question we appreciate a lot because there's 3D printing, additive manufacturing. It's already, from a terminology point of view, a little bit hard to differentiate because technically it's the same, right? It depends who you ask and how it's used. So we use additive manufacturing as part of a solution, which we call the additive fusion solution, or additive fusion technology as a solution. So it has a software play, it has a material play, and it also has the hardware, the manufacturing play. And when it comes to the manufacturing side, there we have the 3D printer, which we actually don't see as a 3D printer. We see it as an additive manufacturing unit, which is an automated system to place fiber tapes. And so this is one part of the solution because there's a second processing step. So the additive part is the automation, the automated placement of fiber materials, and in the right amount, in the right direction. And we can also deep dive on why it's important to place it in the right way, the right amount. But what comes out of this is a preform. That's basically not the final part. It's actually only the material in the right area with the right amount. And this is then transferred into a molding step, a compression molding step, which is a second consolidation step. And that applies pressure and heat in a mold, and really bakes it or fuses it into the final part. And that's why we call the second process step a fusion module, or this is the machine, and it's a fusion step. This also relates to the name of the additive fusion technology. And so the fundamental difference is that we are using 3D printing, additive manufacturing as the automation for placement of the material, rather than only saying it's pure play 3D printing or additive manufacturing, where the final part is coming off the printer or off the additive manufacturing unit.
Gotcha. So you mentioned the material. So what materials are commonly used in AFT, and how does material selection impact the quality, the strength, and the versatility of the printed outcome?
It's a great question, and here again, it goes back to the point that we are a composite manufacturing technology solution, and the additive or 3D printing part is this automation part, which we had in the question before. And knowing composite manufacturing, people know usually if you're in this industry that there's a lot of talk about the material, what's the right material, the different vendors. It's dominated by very big corporations that offer this continuous fiber materials. So coming back to your question, it's not easy to say this material is only good for this application. Sometimes it really relates to the supply chain, to the preference of a customer. And there's there's a wide variety of polymers we are using, from high-end peak pack PI materials, PPS materials, and then goes a little bit down to more engineering style materials, which are because it's nylon materials, PA6, PA12. So we really are agnostic when it comes to materials. So it's really about figuring out the right material for the right application and also the right supply chain, because this is what I mentioned earlier. It's sometimes very important that a customer wants to have a certain material with a certain supply chain.
So can you do multiple materials within a single printed object, or do you have to stick with one type of material?
So we always have, not always, but in most parts, we have continuous fibers materials. So really continuous fibers, really high strength, highly loaded materials, but we also have short fiber reinforced. It's not neat, usually short fiber reinforced areas. So it's a hybrid of short fiber and continuous fibers. In some instances, it's also only continuous fibers, but usually it's a hybrid. And when it comes to the polymers, usually we don't mix polymers. I say usually because it depends. In the printing, in the additive step, we usually don't mix it. But in the molding, as I mentioned before, the additive fusion technology has a molding, consecutive molding step. There we actually do, that's part of secret sauce why we are doing the molding. It's not just the quality check boxes, reproducibility, surface finish, interlaminar bonding. It's also very much about functionalization and design latitude. You can bring multiple materials together, even metal inserts, you can directly bake it and mold it in. So in the second processing step, we do mix materials, different polymer types, but also different, really like all materials, basically, including metals.
Gotcha. All right. So in what industrial or commercial applications has AFT demonstrated significant advantages over traditional manufacturing methods? And what are the main factors driving its adoption in these sectors?
Yeah, when it comes to applications and industries, verticals, which we are targeting, first, it really depends on, I mean, there are different industries that have different customer journeys, different timelines, aerospace being one of them, usually has a little bit longer timeline. So we are like working on aerospace and mobility applications in general, new mobility applications. So new mobility has a shorter time to market. Even there, it could be years for some applications, and it starts with cycling applications, and it goes, and then goes into motorbike applications, all the way to higher-end automotive applications. And it's a lot about metal substitution. And I didn't mention this before in some of the questions, but we are a new technology stack, full end-to-end solution for metal substitution mainly. So it's about enabling the substitution of a metal material, bring it into the composite realm. And this was not possible before because of it could be from a technical point of view, or it could be from a commercial point of view. Sometimes also a combination of both. So it's about enabling metal parts to be produced in composites at scale. So scale means usually a few thousand, could be also 100,000 parts per year. So it's really production approach. And yeah, industries are aerospace, it starts also in more in the interior side, but then also goes into primary structures, the wings and the fuselage of an airplane. But that has fairly long customer journeys or time to markets. So there's different things coming out over the years.
Okay, great. And how does AFT handle like complex geometries and intricate designs?
This is really now starting on the software side. I think that's a very crucial element, which we have not touched base so much. I mentioned it before. So the software play, there are actually two software solutions. One is what we call Fiberfy Design Suite. The other one is Fiberfy Production. The second being more like an MES, manufacturing execution system. That's a cloud platform that connects to everything, basically. It's also the data silo. That's where everything comes together. And it's kind of the workflow system as well. The other side, and this is where, coming back to your question, this is where it starts in the Fiberfy Design Suite. That's the engineering software. Just imagine like a CAD, engineering CAD environment where you have all the different fiber tools to place those continuous fiber tapes, to engineer the material. You also interface with commercial FEA tools, so simulation environments like ANSYS, Abacus, Nastran, like all the big platforms. They could be technically, it's agnostic. It's not limited to any of those. So that's where you engineer the part, where you validate the part, where you optimize the part. And it's a lot about how you orientate those fibers and making sure also that after the molding, the fibers are in the right areas.
Gotcha. And is that software then available in the cloud, on a cloud platform? Is it baked into the hardware itself? How does that work?
Mm-hmm. The engineering software is a standalone software, if you want, and it's local, so it's not a cloud-based workflow or software at this point in time. Yeah, that's where you engineer the part, where it's about lightweighting the part, also about ensuring that the costs are right, that the requirements are right. I mean, this is really like where it all starts and where you invest the time in the beginning.